I just showed you that our metrics is accuracy. In image processing or image classification, in these kinds of problems and tasks, it's okay to use accuracy, but for some specific machine learning problems, like for example, processing sequences, for example, stock market sequences, or so, or for example, processing some data about uh, jobs, for example, what job I have, what job these people have, what color their hair are, or something like that, and classifying them into some categories, where we are going to need some other other metrics, like for example, um, uh, F score or recall or something like that. But I'm not going through that because we don't need that. We are okay with accuracy. So let me do it. Okay. Uh, um, is it record? Okay, it is recording. And before training, we pre-process the data. It is very important to pre-process the data by reshaping it into the shape the network expects it, and scaling it so that all values are in the range of from 0 to 1 in that interval from 0 to 1. So the test set accuracy, for example, there is something we see. For I said that on that MNIST data set, I said that some high performances somehow show overfitting. Overfitting is the gap between training accuracy and the test accuracy. It is an example of overfitting. Overfitting is the fact that machine learning models tend to perform worse on new data on new data uh, rather than on their training data. For example, they perform better on training data. For example, 98% accuracy on training data, but 75 or worse, or 80% or 90 even percent on test data. So we see a gap between the performance on test data set and training data set. So this gap it demonstrates and show us that we have some overfitting. So let's go to the other thing, and we talked about tensors, and we have some zero-dimensional tensors that we call scalars or numbers. For example, 1, 2, 3, 4, they are scalars, and they are zero-dimensional tensors. So vectors are one-dimensional tensors, and matrices, as we know, are two-dimensional matrices. For example, here we see if, for example, if we type x dot endime, it will retain the 3. It shows us that it is some kind of three-dimensional tensor. So, for example, if in this example, 12 is a scalar, a zero-dimensional tensor. So a tensor of rank 0 to a tensor of rank 1 is like a vector, as we see here. Let me let me move the zoom control so I can see. Okay. Sorry. And we have other kinds, as we see here, it is a matrix, a two-dimensional tensor. We have rows and we have columns. But as you see here, it is like we have multiple matrices. For example, if can we have a pen? Oh, sure. Okay, so we should. It is like this. It is it is like this. It is a matrix. It is another matrix, and it is another matrix. Sorry if it is a little messy. I cannot draw good lines. So it is some kind of an extra dimension. It has an extra dimension when we looked at it. rather than, for example, two-dimensional tensors are matrices, but it is a three-dimensional tensor. So let's go back to what we are. Okay, some data tensors in reality, for example, matrices are like this: number of samples, for example, how many samples, and how many and number of features. For example, we have 500 people, and each of them have some columns of, for example, age, hair color, job, blood pressure, something like this. It is like a two-dimensional tensor. So we have number of samples. The number of samples are equal to, in this example, are equal to number of people. So, and time series data or sequence data are three-dimensional tensors. For example, a stock market data set are a kind of sequence data. So, or for example, uh, when we are working on natural language processing tasks or translation tasks, we have some sequences of data. So they are like this. Every when we are working with data, the first parameter here, the first argument, shows the number of samples. And in each example, it is we should know that the first parameter is the uh, number of samples, number of the entries. So, but four-dimensional tensors are images because they they have number of samples, and just pay attention to this part. The other part is another kind of rewriting that first one. So number of samples in images, and after that the height and width. So we have as an image, if for example in Windows, let me show you an example. Uh, for example, okay. For example, I don't know. For example, this file is an image. It is a PNG file. And if I go to the details, we see that 512 by 512 pixels. So it shows us the width and height as we see here, and height and width. And now channels. What is channels? For example, a black and white image just have one channel because it is not an RGB. It is not a colored image. So but a colored image, as the name suggests, it is some kind of RGB image, or sometimes we have some files of CMYK for printing, or RGBA, red, green, blue, and alpha channels. So they shows the channels of the image. So the last argument shows us the number of channels. It is regular. It is regular to see most of the colored images are RGB. So they have three channels: the channel of red, the channel of green, and the channel of blue. So video tensors are five-dimensional tensors. So videos are like images, but they are like sequences of images. So we have number of samples and frames. Frames are the sequence. For example, frame one, frame two, and there are some images in consecutive images behind each other and in a row, so they make a video. And height and width is like an image, and channels is like an image. Just we have some frames, and it makes it five-dimensional. So but most of the problems and most of the tasks we are working are images now. And if we have a video, for example, I download some video from YouTube, and I just extract its frames and makes them into images. I don't feed the video into our our models, our architectures of AI. So it most of the time we are working on images. maybe sometimes, for example, I was working on some kind of COVID-19 data set recently. We are working in a research group, and we have those kinds of CT scan images. They have lots of metadata like the patient's name, the doctor's name, how old are they, what's the problem, so many kinds of things. But we want some parts of it. And we wrote some kind of AI that it categorizes them and it diagnoses them. For example, if someone has COVID or not, and what's good for them to do after that if they have COVID, they have COVID positive. And because we have images of the CT scan and all that data, we created some kind of model that has multiple streams of input. For example, image inputs, and for example, age, uh, maybe some other disease if they have, how old are they, I said female or male, something like that. It is going to affect the decision boundary, of course. So it depends on the data set to create your model. So sorry. Maybe I can just maybe we can go on, but an example of 2D tensors or matrix are, for example, 50,000 people. It is the number of samples, as we see here, number of samples, 50,000, and number of features, or features are in this case are income of that each person, or postal code uh, for their house, and age of that person. So we have three columns. We have three columns, and we have 50,000 rows. Number of samples is 50,000, and number of features, or number of columns, as we say, uh, is three. Every person has three features. So it is an example of 2D matrices. For example, let me annotate here. For example, this is the matrix. They have like, sorry, income, postal code, and age. For example, person one has the income of $1,000 per month, and the postal code is 1123, and his age is 40. So and person two is, for example, he has 250,000 $2,500 per month, and his postal code is, for example, 423, and his age is 21 years old. So it is like the number of features, and we are going to person number 5,000, 50,000, sorry, 50,000. So number of samples, it is number of samples, and they are the features. They are the features here. Let me write, and for example, they are the feature here, and this is the number of samples. So 5,000, 50,000, sorry. So, okay, let's clear all drawings. Okay. And after that, some we have I give some examples of all these kinds of things, but the most important thing we should know here is images. As you see, height and width are the resolution of that image. In that case, I showed you 5012 by 5012 pixels, and number of samples. For example, we have 1,000 or 30,000 or 100,000 images in our data set. So the number of sample is going to be 100,000 images. So 100,000. And color channels, if they are RGB colored images, the color channels is going to be 3 because RGB. So the height, for example, is 5012, and 5012, and the samples is, for example, 10,000 images. So that's it. And let me clear it. Okay. So the geometric representation of deep learning problems is like a twisted paper ball. They are really complicated. The problem is really complicated. As we see, as we are facing the problems, or we are facing everything in our life as humans, it is really complicated. The thing that our brains is doing, but we don't know. It is doing its job unconsciously, so we don't recognize, but we don't notice what it is doing. But it is really complicated, and artificial intelligence or AI algorithms are doing such kinds of things, but they are not mimicking that. They are different. But if we want to give an example, they are a little similar. We just sorry, we just learned that neural networks consist entirely of chains of tensor operations, and all of these tensor operations are geometric transformations of the input data. It follows that you can interpret a neural network as a very complex, for example, here, a very complex twisted paper wall, a geometric transformation in a high dimensional space implemented via a long series of simple steps. In 3D, the following mental image may prove useful. Imagine, for example, two sheets of colored paper, one red and one blue, but put one of them one on top of the other. So now crumble them together, so into a small ball. The crumbled paper ball is your input data. Our input data is like a crumpled uh, paper ball. So, and each sheet of paper is a class of data. So in a classification problem. What a new neural network or any other machine learning model or algorithm is meant to do is to figure out a transformation of the paper ball that would uncrumple it and uncrumple it. And so as to make the two classes, the red paper and the blue paper classes, cleanly separable again. So they can be separable by, for example, a hyperplane or a line. Most of the time, we need a hyperplane. With deep learning, this would be implemented as a series of simple transformations of the 3D space. So, uh, such as such as those you could apply on the paper ball with your fingers, uh, for example, one movement at a time. And uncrumpling the paper ball is what machine learning is about, finding neat representations for complex data manifolds. So at this point, you should have a pretty good intuition as to why deep learning excels at this. It takes the approach of incrementally decomposing a complicated geometric transformation into a, a long chain of a long chain of elementary ones, which is pretty much the strategy a human uh, would follow to uncrumple a paper wall. So each layer in a deep network applies a transformation that disentangles the data a little, and a deep stack of layers makes tractable an extremely complicated disentangled disentanglement process. So you see, uh, this is what we are going to do with our input data. It is like a real twisted, crumpled paper ball. So uh, we have some branches in machine learning and deep learning. So for example, supervised learning, unsupervised learning, self-supervised learning, reinforcement learning. They are the most popular or famous branches and approaches to machine learning. And there are many other approaches there, but we are going to just explain these four uh, approaches because they are the most famous ones. So supervised learning, for example, is the most common case because it consists of learning to map input data to known targets, or as we called labels, or also called annotations, given a set of examples often annotated by humans. So, the examples are annotated by us, by humans. Although supervised learning mostly consists of classification and regression problems, there are more exotic variants as well. For example, sequence generation, syntax tree prediction. For example, syntax tree prediction is a given sentence predict its decomposition into a syntax tree. So, or object detection, maybe in architecture, object detection is what we see most, or in image segmentation is really sometimes we see, for example, in autonomous cars or some other things in architecture. If you want a model to make segments of the scene we are seeing, for example, a photo of a facade of a building, and make segments of that. And so it image segmentation is like drawing a mask on a specific object. So uh, let's go to the next. And unsupervised learning. So let me say, before going to that part, let me give you some examples about, for example, classifications, which is a subset, or a subset of supervised learning, which is categorized under supervised learning. Some classification examples are, for example, detecting spam emails. For example, Gmail uh, does this always for us. It detects a spam email. So, or other things, uh, for example, suggesting for example, if you have a smartphone, iPhone, Android phones, the keyboard is going to suggest other words. If you are typing something, for example, you are typing something, the keyboard is going to suggest, for example, you are typing I am, it is going to suggest fine, I am fine, thank you. So it recognizes the part of the speech or the part of what you typed, such as adjectives, verbs, nouns, and some such things, and it will suggest something based on what you are saying. So it is like a real, some we are seeing some intelligence here. Yeah. For example, other things like a quality control in factories, in assembly lines. Uh, for example, we have a camera above the uh, assembly line, and the lens is toward the assembly line, and each part that is passing through it is being controlled and is being checked by that. And if it is good enough, or it is bad, or it is corrupted or something, and they should just reassemble it or reproduce it, and they should repair it sometimes. So let's go to unsupervised learning, for example. uh, and let me okay, we have classification and regression. Let me give you some examples of regression problems. For example, um, the relationship between the GPA scores and uh, admission and college admissions. For example, if you have a specific GPA score, are you going to be admitted in, for example, in Virginia Tech or MIT or something? It is some kind of regression kind of problem. the data is continuous. They are not discrete numbers or inputs. For example, classifications, they are discrete inputs. For example, emails, a spam or not a spam or non-spam emails are discrete labels. But for example, predicting someone's age by the image, by their portrait, for example, their profile photo on Instagram, but we have an AI that is going to predict their age. It is some kind of, it is a kind of regression problem, because the age is a continuous input, is a continuous value and data. If I'm 12 years old, I can be 12 and 3 months years old, for example. So it is continuous, 12.3 to 12.4, 15.6, something like that. But emails or something like that are not continuous, they are discrete. So let's go on to unsupervised learning here. Unsupervised learning, this branch of machine learning consists of finding interesting transformations of the input data without the help of any targets. We don't have any annotations, we don't have any labels. So it's for the purpose of the data visualizations, for example, data compression, data denoising, uh, or maybe creating some clusters of the data. For example, the Amazon Web Store is going to give us its inputs, or and they asked us to make some deductions and figure out what's the relationship between the sales and the behaviors of their clients. Or for example, in architecture, you can think in architecture, for example, what kinds of, for example, what kinds of facade or element of facade is this, if we have lots of images and we want just to classify, for example, the windows, doors, and what kinds of the door is it, for example, a kind of a facade that is we see most of the time in France or in Paris or in Africa. What kind of the climate is this, based on the building images and such things. Yeah, you can be creative about the problems and those kinds of tasks in your brain and in your mind. You can make lots of these things. If you have the data set, you can be creative enough. And let's go to self-supervised learning. Self-supervised learning is supervised learning without human annotated labels. So it is a little difference between unsupervised learning and self-supervised learning. So, uh, for example, you can think of it as supervised learning without any humans in the loop. There are still labels involved. We have labels here, but it is not annotated by us humans. So maybe we have another AI algorithm to just annotate the labels and the targets, the ground truths. For example, uh, in that COVID-19 research that I was involved, we developed some AI algorithm that just do this self-supervised learning for us. It just see the data set, see the images, and decide if it was positive COVID or negative for COVID, COVID negative or COVID positive. So it's like that. And we have reinforcement learning, and maybe you can go to this deepmind.com. It is now it is a part of Google. It is Google uh, acquired this DeepMind, but it was a British startup, so they were really creative. I'm not going to. So okay, um, and this branch of reinforcement learning recently started to get a lot of attention after Google DeepMind successfully applied to the learning playing Atari games. Do you know Atari, for example? We have some consoles, Atari, Nintendo, PlayStation, those kinds of things, but simple kinds of games. We have an environment and an agent. So, or lately, DeepMind learned to play Go. Go Let me show you what is Go and Go game. Maybe search if I search. Okay. So this is Go game. Asians or Korean people, Chinese people play it a lot, and it is really a complicated kind of game. It is you should be really creative because it is more complicated than chess. So you can imagine how complicated and how hard this game is. And we have Lee Sedol, and some say that um, he is the best Go player in history or of the world. But there was a game, uh, an AI called AlphaGo against Lee Sedol. So he was thinking that I'm going to win this game, and this is what we are going to hear is showing the creativity of AI, how creative AI can be. And some people, because some people believe AI cannot be creative enough, but I think they are not right. If the AI cannot be creative, Lee Sedol would win that game, but Lee Sedol lost to AI. And it was a moment that he was smiling, that he was thinking that I'm going to win this game. Okay, he made the AI made a mistake here in this move, but he said but he lost that game. And he said that I think that there was a mistake from AlphaGo, the AI algorithm. But he said that it was really creative because what humans thought that we are doing some creative things is, it seems that we just do some controversial things, some traditional things. But AI proved that creativity is something that we cannot imagine even, and AI is going to be really creative. So uh, in reinforcement learning, an agent receives information about its environment and learns to choose actions, and that will maximize some reward. So it will do something based on the reward and the amount of that reward, and the agent will try to maximize the reward. So let's back to this kind. Okay, so we have some kinds of algorithms, some kinds of architectures that are called KNN, or K nearest neighbor. For K is, for example, K is 3, 5, 6, everything. So it is a number. Three nearest neighbors, 4 nearest neighbors. It is like that. So we are going to see. Okay, that's it. It is running, and we can go to here. KNN. If you see, okay, here, and KNN is like this. We are going to import our libraries, and this is it. And this URL is the dataset, the link to our dataset. So we are going to import the dataset. It is a dataset of some flowers based on their sepal width or petal width, and some kinds of it. The dataset has 4 features, as we see here: sepal width, sepal length, petal width, and petal length. And there are lots of flowers in that. So we have some columns, as we see here. And as you can see, we import pandas package. Pandas is for working with data frames and spreadsheets like uh, Microsoft Excel files or CSV files, comma separated files, or data frames. As we see here, this is a data frame. So we have, for example, we have 100 samples, and we have five columns or features. And the last one is our class or the label. So the label here, for example, I just type tail and 100. What this does, what this method does, is to just return the last, for example, 100 values, or if I type here 50 or 5, uh, it will return 5 last values or 50 last values. But in this case, I returned 100 last values. So based on these features, the model is going to, as you can see, I read a CSV file that was here, and I just pre-processed it. And iloc is the index location of something, of some values in the data set. I just have all the x and the y is going to be like this. As you can see, I just slice slice the whole data set, the whole number of samples in here, and the whole the first 4 columns or features, as we see here, until the last column. It says that until the last column, from the first column until the last column, and it says that all rows. And here we have all the rows for our y, or the label part, and the last row, as we see here, it is the last row. So and we got just the values. So we have the values, and we are going to split the train test from each other with the test size. As you see here, the test size using the train test split from scikit-learn package is like 20% of the whole data set is going to be the test set. So here, 20% of the whole data set is going to be the test set. Okay. And we have some feature scaling like this. And don't worry about this this notebook. It is not really important, but it is somehow some kind of basics of what we are doing, but it is not really important if you are not going to understand. We have I said that k and n is like a number of nearest neighbors. In this case, I said that nearest n neighbors is going to be 5. So the k and n is going to 5 nearest numbers. And I'm going to instantiate the class k neighbors classifier from scikit-learn package and fit it to our train setup data set. So after that, we are going to have the prediction of that. So ypred is going to be the prediction of the data set. That the data set is going to learn and is going to be trained on our data set in this part. And after that, we are going to have some inferences in this part, in this cell. So after that, you see we have confusion matrix and classification report. So it will, the confusion matrix is like this. There are some measures and metrics, as I said earlier, the F1 score, for example, or recall or precision. You don't have to know these things because we are not going to be to get involved with all of this. But let's go to here. As the thing we have here is a plot that we have this by matplotlib package. In this part, we import matplotlib as PLT. So we draw a diagram or a chart. And as you see here, as the k value of the neighbors increases, the mean error is going to be increased. So the best value, I think, is around here. So you know, these are the best. But which one is the best k value? I think when the k value is lower and smaller, it is the best, because in these parts we have zero mean error. So it is the best performance we got. But when we have lower k numbers, the model is performing better on our data set because it is less complicated. It is less complex model. So it is not going to overfit. So let's go back to our sorry, our presentation. As we see here, if the k equals to 3, this data point is going to be classified as class B, or the purple point, purple class, because we have two purple class here and one purple one yellow class here, or class A. But if we just increase the numbers of the k, we are going to see that it is going to be classified as a class A, this data point that we are going to decide about what we should do to this. You see the difference between the k values here, but when we have same mean errors, the best performance is on a smaller k values. So it is a kind of machine learning or classical machine learning approach to AI, but we are going to use deep learning most of the time. We talked about deep learning, but it is okay to know such things, because sometimes it is not necessary to work with some complex models in deep learning. We have some deep networks, so we can just solve the problem with such simple networks and architectures, as for example in this data set, for example iris data set. Let me show you if there are some images of it. Okay, so as you see, it is for example the data set contains some flowers like this, but we just have some features of that. We don't have any image of that, and it is going to decide which flower is going to belong to which class based on its features like petal width and length and sepal width and length. So in these situations that the classification or regression or the problem is not that complex, we are not going to use deep learning. So that's okay to use some simple machine learning and simple machine learning algorithms. So um, so you know, I told you that we normalize the values to uh, to the interval of 0 to 1. So it is really important to pre-process the data to normalize the data. So the reason of the normalization is, since the range of values of raw data varies widely. For example, some features, for example, in that, let me go up here. Where was it? Okay, here, uh, for example, we have this. Let me, we have this, and for example, we have income and postal code and age. So age is going, for example, to vary from 1 to 100. For example, maximum a person can live for 100 or 80 years. But the income is going to, for example, from $1,000 in months to, for example, 4,000. I don't know, 10,000, $10,000. So you see, they vary in their scale. So they are from 1,000 to 10,000, and here we have from 1 to 100. So they are not in the same scale. So, and if we have the postal code, for example, the postal code for my house is like, for example, 123. For your house, it is like 2, 5, 6, 7, 1. So you see there are really different numbers. So when we so let me go back to there. Okay, when we just normalize the values in some machine learning algorithms, objective functions will not work properly without normalization. For example, the majority of classifiers calculate the distance between 2 points by the Euclidean distance. If one of the features uh, has a broad range of values, in that example, for example, the income feature has a broad range of values, but the age doesn't have a broad range of values. So the distance will be governed by this particular feature, it will be governed by that particular feature. So therefore, the range of all features should be normalized so that each feature contributes approximately proportionally to the final distance. So that's the reason we should do this. We have to do this. And the gradient descent algorithm, which is used in neural network training and other machine learning algorithms, also converges faster and with normalized features. And this is another reason. So we have some biological neurons, for example, in our brains. There are millions, I don't know, maybe billions of neurons. So they are something like that. They have some inputs. Uh, they got the input from dendrites, and they will process the data. They will process it, and learn what's going on. And they have some outputs. We we see some similarities between neural biological neurons and some artificial neurons, but they are not artificial neurons are not mimicking it. So uh, in plain English, a single neuron will pass a message to another neuron across the interface if the sum of the weighted input signals from one or more neurons into it is great enough. For example, to cause the message transformation, we have some for example, we have some inputs here, and we are going to process the data and the inputs in here. And if it is great enough, the value is great enough, it will cause the message transmission, and we have an output here. So that's what we have uh, in in neurons in plain English. I'm not going to make it complicated or make it complex, make it hard. So uh, we have, for example, in artificial neural network, it is like a diagram of a simple neural network. We have some input layers, some hidden layers. In this case, we have just one hidden layer, and we have two output layers. For example, in artificial neural networks, the activation function, what we see here, for example, in this part, we have some activation functions, and we are going to process the data, and the neuron is going to process the data with activation function. So the activation function of a node, this is a node, defines the output of that node given an input or set of inputs. So we have like lots of inputs here. So it will decide whether to cause the message transmission or not. So this is like some neurons in a layer and some neurons in another layer and some other neurons in the output layer. So for example, the simplest activation function we have is, for example, like this. If the sum of the values, for example, is going to be a positive value, value, so the output is going to be 1. And if the sum of the values, some of the inputs in the activation function is going to, is going to be, for example, 0 or less than 0, the output is going to be 0. You know, if uh, it is positive, the output is 1. And if it is negative or 0, the output is 0. It is the simplest activation function we can use. So, but there are other complex and other more powerful activation functions we are going to see. So we have these kinds of outputs and activation functions. As I said, for example, in this case, if the activation function, the result of that is going to be 0, so the output is 0. If the activation function results 0, the output of that neuron is going to be uh, 0.5. And if the result of the activation function is going to be a positive number, the um, the result, the output of that node or neuron is going to be 1, as you see here. But it makes some problems that we are going to see. For example, activation function, as you know, activation functions decide whether a neuron should be activated or not by calculating weighted sum and further adding bias. We have a bias here, and um, with it, the purpose of activation function is to introduce nonlinearity into the output of a neuron. So we are going to higher dimensions of mathematics. So, for example, in this case that I told you, where is it? In this case, okay, in this case, the problem is really like a crumble twisted paper ball. So we are going to go to higher dimensions. So it is going to be separable by a hyperplane. So the main purpose of activation functions are to introduce nonlinearity to the output of a neuron. So it makes it simple to just separate those classes. So sorry. So, and as we see here, cost function. So we have cost, yeah, okay. We have cost function. Cost function is a matter of how good a neural network did with respect to its given training sample and the expected output or their labels. It also may depend on variables such as weights and biases. So you know we have weights, we have inputs. Let me write it. We have inputs, a set of inputs. We have weights. Let me write it in another color. We have weight, and we have a bias. A bias is because of this linear equation. If we don't have bias, sometimes we will it will result in some kinds of these kinds of line, a flat line, a horizontal line that is not uh, like a diagonal line. We need diagonal lines. So if we have something like a bias, it will be something like this or this or this. So a bias is doing these things for us. So the cost function is a measure of how good a neural network is performing. A cost function is a single value, so it is like a number. It is a number, not a vector. It is a scalar. It is a number. because it rates how good the neural network did as a whole. And cost function requirements must be able, the cost function or C, as we see here, must be able to be written as an average. As you see the formula, it is an average formula. So over cost functions of C, X, for example, for individual training examples X, we have this, you see, CX. So let me clear it. Okay. So this is to allow us to compute the gradient with respect to weights and biases for a single training example and run gradient descent. So sorry. The cost function C must not be dependent on any activation values of a neural network besides the output values. So you should pay attention to this. And we have some loss functions, for example, L1 or L2. L1 is going to be MSE and MAE. It is the short form of uh, mean average error and mean squared error. So see that the formula suggests this, but using this is in most cases is better, but most of the time we are using L2 or MSE. So but in some regression problems or some machine learning problems, we need to use a specific cost functions, maybe MAE in that case or MSE. It depends on the situations, but most of the time that in this workshop, we are using MSE most of the time. So let me, okay. So we have another cost function that is called cross-entropy. It will allow us it will allow the network to converge faster. And if the difference between the predicted results and the ground truth is bigger, it will the neurons and the nodes are going to learn and are going to be trained, are going to train faster. So it will make the training phase faster, cross entropy. As you see the formula, you don't have to know the formula. I just write it if you are curious, but you don't have to know the formula because all of these parts are going to be done by the frameworks like of TensorFlow or PyTorch. So you don't have to know mathematics. So don't worry. Don't be scared about these things. It is just to know how they work. So you grasp the knowledge, you know, you learn the ropes good enough. Because as I said earlier, some people say that I'm an AI enthusiast or I'm familiar with AI, but when you talk to them and you said how this network that you created is working or how you can make it better, they have no idea. So knowing these things are going to help us know better, are going to help us have better ideas what's going on under the hood. So it's for it, and this is it. So and gradient descent and backpropagation. So we have gradient descent is a first order iterative optimization algorithm for finding a local minimum of a differentiable function. So functions like these, as the diagram here, is a differentiable function, or these are differentiable function. But we have sometimes we have global maxima or global minima or local minima. Sometimes the algorithm is going to be stuck in local minima or saddle points. We should be careful, and we have some strategies for these problems. So there is no worry. But gradient descent is a first order iterative optimization algorithm for finding a local minimum of a differentiable function. So the idea is to take repeated steps in the opposite. As you see, uh, the function is going this way. So the function is going this way, but we are going to that way, the opposite side. So it is going to, at each step, it is getting smaller, as you see. So until we reach the global minimum for the loss function, for the error, for the cost. So the idea is to take repeated steps in the opposite direction of the gradient. So or approximate gradient of the function at the current point, at this point and that point. So because this is the direction of the steepest descent, the steepest descent or global minimum is here. So we are going to get through this, and we are going to just use it to train our network better. So let me clear it. Okay. Uh, but finding global minimum is not as easy as in this function. Most of the time, we have some functions like this. You know, they are complicated, and we know that global minimum is here. But sometimes the gradient descent and back propagation is going to be stuck in here. But we have something like momentum or some other things that will solve the problem for us. So let's go to the other. Okay. So this is a neural network works, as you know. Let me. Oh, okay. I haven't explained backpropagation. Backpropagation, short for backward propagation of errors. Uh, it is an algorithm for supervised learning of artificial neural networks using gradient descent. So, uh, given an artificial neural network and an error function, the method calculates the gradient of the error function with respect to the neural network's weights. So, know how it is working. So, uh, a neural network in a nutshell is going to be like this. It is a neuron. So here we have a neuron, and we have the inputs in here, x input, x1, x2, x through xn. So, and we have our weights corresponding to inputs. So we initialize our weights randomly, and we have an x0 equals 1. So it is our bias. So x0 is bias. So that's it. And sorry, as you see here, we have in a neuron, we have an activation function and the sum of those inputs and weights and bias. So uh, let me choose a better, maybe this, no, this is better. So, and it will calculate something, and it will throw the result, the output, and we have some output here, for example. So the output is going to be backpropagated through the gradient descent and the optimizer, and it is like a, a signal or a feedback to the network, to the weights. So the optimizer here is going to update the weights and a little in every iteration. In every iteration, we are updating the weights a little bit, so the network will be trained better. You know, it is how a neuron works. So this is a neuron, and there are inputs and weights and all the things, and you can just imagine it in a network like here. For example, in this we have lots of inputs and weights and other things, and the outputs of every uh, neuron. So okay, so we have some frameworks, you know. For example, as we are going to work with Python, with TensorFlow and Cross. TensorFlow and Cross are merged together, and I remember that, for example, maybe some years ago, we have some Cafe or Sunny or Chainer or Microsoft. Microsoft has uh, its own framework for AI or deep learning things. But nowadays, the pioneers are Cross and TensorFlow. But Cross and TensorFlow are the most popular one. For example, TensorFlow GitHub. If we go to the GitHub repository of TensorFlow in here, uh, you can see that they uh, they have 160,000 stars. People have made it is like they liked it for 160 times, 60,000 times. And uh, PyTorch, let me move the Zoom controller. So PyTorch. Okay. And let me, okay, they have like, you see, 52,000 likes or stars. So they are the most popular, but um, this popularity will help us because they have a great community, lots of developers. If you have any problem, you can ask them. But these kinds of uh, frameworks are not used by so many people, but because they are some kind of vanished or forgotten because they were not good. But PyTorch and TensorFlow are really good. They are fast, they are easy to use. They do that, for example, these things that they are doing under the hood, that we just don't worry about these things. We just define something and it will do the job. So it's really simple, you know. And I just put some images here. It is from Francois Cholet tweet. I remember that he tweeted something, he posted something, I posted something. And about, for example, uh, a single, an algorithm that is implemented in Cross, TensorFlow, PyTorch, and Cafe, I think, and some other frameworks, and they compared it. You see that they are really the same. There is not a lot of difference here, but they are something like the community and how fast and how uh, consistent they are is going to make the differences. And in this case, TensorFlow and PyTorch is going to make it easier for us. And we are going to use TensorFlow. So uh, now let's have fun, yeah? And let's see something that, for example, let me move it. Okay, so this is a TensorFlow Playground. So you will go to see what's going on visually. For example, if the problem type is classification, and let's have the activation as linear, for example. So you see there is a linear function here, linear function here, linear function here. The input is like this, and we can use the data and other kinds of data. For example, this, and I'm going to start with this one. And we can add some layers here. It is just a visualization to get familiar with how they work. So, and I can just add some neurons, and I can just, for example, add some to this. And let's let's train it, for example, and let's set it, the learning rate is okay. I'm not going to change these things. I just hit this button and let's see. You see, it is converged because we see a nice, good line that is fit to our data set. So they are separated by a line because the problem here is a linear separable. I'm going to just pause it. It is a linear separable kind of problem. So we are going to do this, for example, and start it with uh, a linear activation, the simplest activation function. And you see the test loss and the training loss is not going to change. We are not seeing, although the epochs and the iterations are increasing, but we are not seeing any change in our loss. And maybe we can add some neurons or we can add some layers, but there is no difference. As you see, each neuron is contributing to the whole network. For example, this neuron is going to um, draw a line like this. This one is going to be like that. So, you know, if every and each one of them are going to just do it linearly. They are linear because the activation function is linear. But what if I set it to ReLU? ReLU, we have not. I didn't talk about ReLU, but we are going to learn about it. So learn it, and let's see if, for example, you see, it is going to, yeah, it is converging. It is converging really fast. Iterations here, and you see, it is really fast. So the activation function is adding some nonlinearity. As you see here, it is not going to be linear. Every and each one of them has some kind of nonlinears. So what if this was the problem? So let's start it once more, and you are going to see this. Yeah, the first, for example, the first neurons are going to be like this, two vertical or horizontal lines, but they are the other lines, the other neurons are going to learn some other features. So for example, this one is going to be like drawing some line like that, and for example, this one is drawing something like that, and it is going to be a little bit okay because it is a complex kind of problem, but it is going to, I think, solve it. Maybe let's see. Um, the problem is really difficult. It is not simple, so it takes a lot of iteration. So as you see, you see the progress, and you see how it is moving, and here, in here. So you see, let me send this in the chat box. So, okay. So as you see, it is converging, yeah? But if it was a linear activation, it will never converge. Even in simpler uh, uh, data sets like this one, linear is going to do just good enough and good and well. It will perform well in uh, linear problems, but in these kinds of nonlinear problems, they are not going to converge. So we should change the activation function, as in this case ReLU or Tonnage or Sigmoid, but we should add some nonlinearity. So you see the effect here. So I'm going to stop it. Okay, we see that it will converge, but I'm not going to wait for it. So okay, and we have in this part evaluating the model and training and validation and test set. So we are going to have a training set and a test set and a validation set. A validation and a test set, we are going to know what is it. In machine learning, the goal to achieve models that generalize. We don't want them to overfit. We just want them to fit the hyperplane well enough, but not to overfit. We just want them to make a balance, to have a balance between generalizing and fitting the line without overfitting or underfitting. So the goal is to achieve models that generalize, that perform well on never before seen data. And overfitting is the central, as it is the main obstacle. You can only control that which you can observe. So it is crucial to be able to reliably measure the generalization power of your model. The following sections look at strategies for mitigating overfitting and maximizing generalization. In this section, we are going to focus how to uh, measure generalization and how to evaluate machine learning models. So, sorry. So the reason is that developing a model always involves tuning its configuration. For example, choosing the number of layers or the size of the layers. We call these things the number of layers and the size of layers, the number of the neurons in a network, in a layer. Sorry, in a layer is called hyperparameters. So hyperparameters of the model. So we will choose the number of the hyperparameters, and don't mistake hyperparameters for parameters, which are the network weights. Network weights are parameters, and network hyperparameters are the network's layers and the size of the layers. So don't mistake these two. Uh, you do this by tuning, by using you do this part of tuning by using as a feedback signal the performance of the model on the validation data. So we have a validation set. We just cut the data set into a training set, a validation set, and a test set. So central to this phenomenon, but there is something that we should be careful when we just split the data set into validation set and training set and test set. Uh, Central to this phenomenon is the notion of the information leaks. So information leaks, every time you tune a hyperparameter of your model based on the model's performance on the validation set, some information about the validation data leaks into the let me say uh, leaks into the model. If you do this only once for one parameter, then every few bits of information will leak, and your validation set will remain reliable to evaluate the model. But if you repeat this many times, uh, running one experiment, evaluating on the validation set and modifying your model as a result, then you will leak an increasingly significant amount of information about the validation set into the model. So, you should be careful about these things. Your model shouldn't have had access to any information about the test set, even indirectly. So information leaks are bad for our models. This is the simplest evaluation protocol, and it suffers from one flaw. If little data is available, then your validation and test set may contain too few samples to be statistically representative of the data at hand. To address these, we use k-fold. And what is k-fold? So this is k-fold. We have some folds, some chunks of the data, as you see here, and in each fold, uh, we just split the data in we split the data into k partitions of equal size. For example, several partitions of equal size, so they are equal in size. For example, um, for each partition, I train a model under for each partition of I, for example, uh, each partition of I, for example, these things. So, sorry, train a model on the remaining k minus one. So we are going to run the model on this part and this part and this part, and after that, and we are going to evaluate the model on partition I. So we have the partition I, this here. So after that, our final score is the average of the k score. So after that, we have trained our model on this part and this part, the second part, for example, the third part, the fourth part, the fifth part, and uh, our final score of the model is going to be the average of those k folds, k number of scores obtained. This method is helpful when the performance of your model shows significant variance based on your train test split. So, you know, when it is good to use k-fold in this situation. And iterated k-fold, we have some iterated k-fold with shuffling. So this one is for situations like in which you have relatively little data. So you have really little data available, and you need to evaluate your model as precisely as possible. And it is extremely helpful in solving the problems in doing these kinds of things. And it consists of applying k-fold validation multiple times and shuffling the data every time before splitting it splitting it into k ways, for example. The final score is the average of the scores obtained at each run of the k-fold validation. So no and so so we should keep something in mind. For example, um, data, we have something as we call data representativeness. So we want both our training set and test set to be representative of the data at hand. For example, if you are trying to classify images of digits as we have in MNIST dataset, and you are starting from an array of samples where the samples are ordered by the classes, uh, taking the first 80% of the array as your training set and the remaining 12% as your test set will result in your training sets containing only, for example, classes 0 to 7, whereas what your test set contains only digits 8 and 9. So you see what's going on here. This seems like a ridiculous mistake, but it is surprisingly common. So for this reason, you usually should randomly shuffle your data before splitting the data set into training set and test sets. So, and the arrow of time, sometimes we have sequences uh, that the time is important, or the time is has some effects on our data set. For example, if you are trying to predict the future given the past, for example, tomorrow's value of some stock in the stock market, or tomorrow's weather, or stock movements, and such things, you should not randomly shuffle your data before splitting it, because data matters here. The array of data, I'm sorry, the time and the arrow of time matters here because they are sequences. We cannot just shuffle them. So it matters to pay attention to uh, what kind of data set you are working with. It is really important to know your data set. And redundancy in our data set is another thing that is important. If some data points uh, in our data appear twice, for example, that is common in real world data sets, that some parts of the data appear twice or three times or more. Then shuffling the data and splitting it into a training set and a validation set will result in redundancy between the training and validation sets. In effect, you will be testing on part of your training data, which is the worst thing you can do. And we should make sure that our training set and validation set are disjoint. So, and sorry, uh, where is it? Okay. Data preprocessing for neural networks um, aims at making raw data at hand more amenable to neural networks. This includes, for example, vectorization, normalization, handling missing values, because in real world data sets, we have some missing values sometimes, and feature extraction. And for example, a for example, vectorization is, for example, this all inputs and targets in a neural networks must be tensors of floating point data. It is really important that all inputs and targets in a neural networks must be tensors of floating point data. Sorry, or in specific cases, tensors of integers. But most of the time, we should have tensors of floating point data. So uh, whatever data we need to process, for example, images, sound, text, uh, numbers, everything, we must first turn it into tensors, a step called vectorization. We do this part by using NumPy, so it is okay. We don't have to be worried about this. Most of these things are just going to be done by using frameworks and libraries. For example, in value normalizations, for example, as I said earlier, in the digit classification example in the MNIST dataset, for example, you started from image data encoded as integers in the 0 to 255 and encoding grayscale values. Before you fed this data into our network, we have to cast it to float 32, to floating point numbers, and divide them by 255 because we want to normalize it. So we end up with floating point and values in the 0 to 1 range. So, uh, feature extracting, and it is making a problem easier by expressing it in a similar way. For example, in this example, we have a clock and we want to represent it. So if the raw data is like a clock itself, so uh, but we want to represent it better to fit it into our uh, model. So maybe a better representation of that data is like this: some polar coordination system or some Euclidean coordinate system. But maybe the best thing we can have is like this. For example, theta 1, 45 degrees, and theta 2 is 0 degrees. So it is the hours and it is the minutes. So it is better to have a good representation of our data set. So the model uh, will be trained better. Uh, and Uh, okay, so we have overfitting and underfitting. It is really important to pay attention to these things as we have underfitting and overfitting here. Okay, so let me just do it. Okay, see here, it is a well-fitted line, and that separates most of the data points well enough. But we have some uh, mis misfitted values. But it is good. It generalizes enough. If we have other data sets, it will generalize enough. But we have underfitting, as it is not fitting good enough, well enough, and overfitting that it must do its job perfectly. We don't want neither underfitting and overfitting. So um, the fundamental issue in machine learning is the tension between optimization and generalization. So, you know, there is always a tension between them. Optimization refers to the process of adjusting a model to the best performance possible on the training set. So, uh, to prevent a model from learning misleading or irrelevant patterns found in the training data, the best solution is to get more training data. A model trained on more data will naturally generalizes better. And when it isn't possible, the next best solution is to um, modulate the quantity of information that our model is allowed to store, or to add constraints on what information it is allowed to store. So the processing overfitting, the processing fighting overfitting is called regularization. So regularization is fighting overfitting and making our model uh, generalize better. So let me just clear it. Okay, it's cleared. The screen is cleared. And we have AGI, ANI, or Super AI. There are some stages of AI. Now we are in uh, the first stage of AI. That is, for example, it is focused on a specific task. Every AI, every algorithm, every model is specifically working with a specific task. For example, we create a model to just classify some images or to generate some images. It is not going to work with text, with sound, with such things. And but in general, AI, that maybe we reach it in the near future, maybe not. We are not sure. Scientists are not sure about it. Uh, an AI and a model is going to do what humans are doing now. The performance is equal to a human, and it can do everything like a human. We can do everything. We can look at things and say that it is a dog or it is a cat, or you are my friend, you are my father, everything. We can talk to you. We can uh, grab for example, mm, a glass of tea and drink tea. We can do everything. So that is general AI. If an AI can all the things we humans do, but we have some super AI that is going to be super intelligent. So uh, it will exceed the limits. Maybe we are not sure. We are in narrow AI, but maybe someday we reach super AI. So that's the three stages. So that's it. And um, overfitting and underfitting have some solutions. For example, regularization is the solution, and reducing the size of the network or the capacity of the network uh, to prevent overfitting is another way to fight overfitting. The number of learnable parameters in the model, which is determined by the number of layers and the number of units per layer, um, uh, that's it. So in deep learning, the number of learnable parameters in a model is often referred to as the model's capacity. So intuitively, a model with more parameters uh, has more memorization capacity, and when it memorizes the data, it will overfit, and it will easily learn a perfect dictionary like mapping between training samples uh, and their targets, a mapping without any generalization power. At the same time, keep in mind that we should use models that have enough parameters that they don't underfit. Your model shouldn't be starved for memorization resources, and it should not overfit. So neither of them is not good. We just want a good fit line, a generalization, a good generalization power. There is some compromises to be found, too much capacity and not enough capacity. And there is no magical formula for that to determine the right number of layers or right size for each layer. They are hyperparameters. That's why we call them hyperparameters. You must just evaluate an array of different architectures. For example, on your validation set, not your test set. Pay attention to this. On our validation set, we do these things. And in order to find the correct model size for our data. So we should just tune the hyperparameters and just um, to determine the right numbers of the layers and the sizes of layers, because we don't know at first, we don't know what's good for that. So they are hyperparameters. We should fine tune them. We should tune them. And sometimes adding a weight regularization is another kind of fighting overfitting. So a common way to mitigate overfitting is to put constraints on the complexity of a network by forcing its weight to take only small values, which makes the distribution of weight values more regular. This is called weight regularization, and it is done by adding to the loss function of the network a cost associated with having large weights. The cost funcs the cost comes in two flavors: uh, L1 regularization and L2 regularization. You don't have to know more about this. And there is something I like uh, really a lot about the next strategy, that is adding dropout. What is dropout and adding dropout? Dropout is one of the most effective and one of the most commonly used regularization techniques for neural networks, developed by Jeffrey Hinton, as we know, that famous professor at the University of Toronto. And he's a student at the University of Toronto. So dropout applied to a layer consists of randomly dropping out, or what we say, setting to zero, a number of output features of the layer during training. So let's say a given layer would normally return a vector, for example, a vector of 0 0.2, 1.3, 0.7, 1.1. And for a given input sample during training, after applying dropout, this vector will have a few zero entries distributed at random. For example, let me type it. The first, uh, the normal return value of the vector is, for example, 0.3 and 1.4 and 0.7 and, for example, 0.1. And after applying dropout, it will return something like that, 0, 1.4, and 0.7. And what is this? Okay, it is 1.1 and 0. So it sets those features to 0. It just randomly drop out though a number of output features, So uh, um, we usually set the value of dropout between uh, 0.2 and 0.5 or 20% to 50% of the neurons. So it will set 50% or to 20% to 50% of the neurons to 0. So that's it. Let's go and see this. Okay, what's the overfitting and underfitting? Okay, overfitting and underfitting. As we see here, we imported our libraries and we just load the dataset, the IMDb dataset, that movie rating website. And we just imported and loaded 10,000 entries. And after that, we have, I'm going to just, you can just see what's going on. We just vectorized the inputs. And at first, we have a layer, a network of, for example, 1, 2, 3, a three-layered network. As you see here, we have the input shape of 10,000 as this. We should pay attention to it. And the activation is ReLU. And we have 16 neurons. And the layer is a kind of dense layer. It is a fully connected layer. All the neurons are going to be connected to the other neurons. For example, this is going to be 16 neurons, and the next layer is like 16 neurons in this part, and they are going to be connected fully. They are fully connected. All of them are connected to each other. So it is like this. It is like something like messy as this. So, and the activation is ReLU. We are going to learn what is it. And the input shape is like that. 10,000 by nothing. It is a vector. So, but if we have some images, as we will see, you are going to see what is going to be the input. So at the end, we have sigmoid function. As you see, let's go back to our PowerPoint, our slideshow. Let's see. Okay, the activations. Where are the activations? Okay, this is the something like this. The shape of sigmoid is like this, but sigmoid is going to be like this. It will output from 0 to 1, just this. So we see something like that. And when we have sigmoid, so it is like a binary classification, as we see here, binary cross-entropy, and the optimizer is RMS prob. So the metric is going to be accuracy. And you see, we have just one neuron because it is a binary classification. It is either 0 or 1. We have not any other. What does it mean? Because this is an IMDb dataset. So the reviews are like this. I like this movie or I don't like this movie. If I like this movie, the output here is going to be 1. And if I don't like that movie from that reviews, not me, other people reviews, the output is going to be like 0 if I don't like, if I like 1. So that's it. And now we just created this model and created a model with a smaller capacity. So we have just 4 neurons in our input layer. This is our input layer, and this is our hidden layer. And we called it a smaller model, and original model is this, and a smaller model is this. So we are going to fit the original model. As you see, we are going to fit it on our train set, uh, the inputs of the train and the labels of the train. And for 20 yeah, for 20 iterations, and the batch size is 512. And the validation data set, as we called, as we see here, we have some, we talked about, we talked about validation data set and training data set. So um, what we see here, validation data set is going to be the test set of the data set, you know. So let's see how good it performs. So the validation accuracy is 85% on this on the original uh, model, on the original model. So we have, for example, 85, yeah. At last, in the end, we have 85. And on a smaller model, let's see how good it performs. So it is really the same. You see, we reduced the capacity, but let's go on and see what's happening if we do something else. As you see, we have plotted this thing. We just uh, draw some figure, and we see we have the original model. As you see, the validation loss is going to increase so much. And we have the smaller model, as we have here. It is not going to increase that much, but they are performing at this point the same. Their best shot is on epoch, for example, epoch 4, maybe. So I think epoch 4. So let's go. And so, okay, let's see. Yeah, 6 epoch versus, you see, 6 epochs for a smaller model and 4 epochs for the original model. So a smaller model is performing a little bit better. But let's say, let's see a bigger model. So we have 512 neurons in our input layer. In here, this is our input layer. And for our hidden layer, first hidden layer, we have another 512 neurons. They have just a ReLU activation function, and the input shape is 10,000, as we have here, because we have 10,000 entries. So let's go to this bigger model. Yeah. And in the last layer, we have just a neuron and sigmoid. Sigmoid is going to output something, give us an output of either 1 or 0. So that's it. And let's see what's going on here. So in the last, after 20 epochs, we have 86, somehow 87, 88, 88, 89, but in the last we have 86. So and the accuracy on the train set, it is accuracy on the train set, and it is the accuracy on the validation set. So we just want the accuracy on validation set, because we want to just measure it on the validation set. It is more important than the accuracy of the training set. Validation set is more important. the performance of the model is. So you see here, the original model is like it is like these stars, and the bigger model, as you see, I think just one epoch, yeah, here, just one epoch, and it got overfitted. So that's really bad. So it is really more, it has more power than what we need, you know. And this is the loss. It was the validation loss, and it is the training loss. As you see, it has lots of variants, the big model, but the original model is more consistent because the capacity is really uh, yeah, it has a lower capacity, but the bigger model is like an overkill. It has lots of capacity, so we don't want that. So let's do we import regularization function here from TensorFlow Cross. So we want an L2 model, an L2 regularization in this port, and let's say kernel regularization. You see, we just add something here, and as you see, we just add regularization of 0.001 value and another regularization of the same value to our model, and let's see how it performs. You see, it's much better. The original model is like this. The validation loss is going to increase, but the validation loss of the L2 model is not going to increase a lot. So it is better. We mitigate overfitting better. So let's have regularization of L1 and regularization N1 and L2 at the same time. This is some kind of let's say function that has both of them at the same time. So and now we add dropout to our model. You see, uh, this is our model, and I called it DPT model because of the dropout. And the output is like, uh, yeah, the dropout will set the 50% of the neurons to 0 randomly, and this is the same here for this layer, for the hidden layer and the input layer. So let's see how it performs. So as you see, it has better performance, but in this case, the best performance was to L2 regularization. So you can just run this code on your local machine to see the results. The results are not going to be exactly the same to what you see here, because I ran this code, I executed the code earlier, a couple of months ago maybe, and we know that the weights are initialized randomly, so we are going to get some so we are going to get some random results, but they are not that different. They are a little different, and we are going to see a little difference between my results, as you see here, and your results. So, but they are not going to be exactly the same. A small difference between our result is okay. So, but big differences maybe show that there are some problems with the code or with your system or with how you executed it. Okay, so let's get back to our let's where we here we are. Okay, I'm going to just let's see. Uh, sorry. I talked a lot and yeah. So this is and okay. So um, we have convolutional neural networks or CNNs, and they they are doing this hierarchical. They have a hierarchical system, and we heard and you heard. I think that you heard about convolutional neural networks a lot these days because they are the most famous kinds of neural networks nowadays uh, in image processing. So uh, if we have, for example, lots of layers, if we have a deep neural network and we have lots of layers, the first layers, for example, a couple of first layers, are going to learn the low level features. As for example, in this case, let me just do this and you see. Okay, in this case, low level features. What are low level features? They are, for example, like lines, diagonal, horizontal, vertical. There are some edges, maybe some differences between pixel values, something like that, you know? Let's just this or this or this. But middle layers that they are, for example, in the middle of the network, they are going to learn more sophisticated and uh, more complex features. As in this example, for example, they are going to learn this. You see, for example, this headlight, and we see this headlight here, a piece of it, or maybe some kind of textures, special textures here. They are going to learn some more sophisticated, but high level features in the last layers of our network is going to be something like this. In our in our convolutional part of the network, because we have some convolutional part of the network and we have some classifier part of the network. And in our last layers in convolutional neural networks, for example, you see, for example, here, it is like the wheel here, for example, maybe this one. Let me clear it. Okay, let's say this one, for example, is like this. They are learning and it is trained some on some sophisticated, so the it is going to be beneficial for us, these things, these three parts, as you see. And I'm going to tell you what is the benefits of having and knowing these things. Maybe you say, so what, and if I know these things, so what? But we are going to know what is going to uh, work for us and what is beneficial. As you see here, for example, this is another example of that. So let's go to that. And I will just, there were an example. I will just send you the link. You can see how a brain or how certain neurons of a cat's brain will respond to the will respond to a specific lines, for example, a specific diagonal line. So uh, let's say, uh, sorry. And there is a problem with fully connected neural networks. You see, if a fully connected neural network like this, every neuron is going to be connected to the successive neurons. So if we have an image of for example, an image of a dog, that the width and the height is 1,000 pixels. So the height is 1,000 pixel, the width is 1,000 pixel, and we have three channels of RGB. We have three channels of color. So the parameters are going to be like 3 million. We have 3 million parameters for the input layer. So it is a lot of parameters. And what if we have 1,000 neurons, for example, in our hidden layer? So it will blow just our mind that how many layers are going to be connected and how many neurons are going to be connected, and it needs lots of computational power. So this is the problem. They need this is the problem with fully connected networks. They need lots of computational resources. So but we have convolutional layers and filters. This is a convolutional filter, and as you see, for example, we have 1 1 1 0 0 0 -1 -1 -1. What it does is like this. For example, 1 1 1 is like uh, for example, a white line, for example. And what this is going to do is like a black line, and these parts are going to be, for example, some value pixels without values, for example, some non-important pixels. So it will just go over the filter. Let me just clear it. Okay, the filter, the convolutional filter, as we see here, this filter, this is this filter. So is going to be run over our image. So it will go on this part, and then this part, and then this part, and this part. So it will do this. For example, if I play it, you will see how it is going to work. And the result will going to be a convolved feature. It just like uh, just it is the sum of those features together. As you see, the filter, the convolutional filter, is like 1 here, 0 1 0 1 0 1 0 1, and it is going to be a sliding over our images and our inputs, and we have we will have some values, and we are going to use it, and we are going to mitigate the problem of with convolutional sorry, with fully connected networks by using convolutional neural networks. They are really great. And for example, we have this channel, and we have an image of 6 pixels by 6 pixels and 3 channels. So we are going to multiply it or run a convolutional filter, not a convolutional filter, but 3 convolutional filter. Why 3? Because our image has 3 channels here, RGB, for example. We have 3 channels, and we have 3 filters. Each filter, a filter for each channel, each color channel. So as you see, we have a 3 by 3. It is the size of the filter size, and it is the depth of the filter or the number of the filters. We have 3 filters, and we end up with a 4 by 4 picture. So image, sorry, a 4 by 4 image. And you see here, we have this picture, this image that is colored RGB, and we have 3 filters because we have 3 color channels, and we are going to slide it and move it over our image. So we are going to do this, and we end up with a 4 by 4 image. So we have some edge finding. We have some edge finding filters. as we see here, let me just make it bigger so you can see. We have some, for example, as you see here, these filters are like this. You don't have to need these filters, the numbers. It is just here to tell what's going on. So, and for example, other edge finding, some of them, for example, based on the formula, you can know what's going on. This edge finding based on the formula is going to detect vertical lines, and it is going to detect horizontal lines better. So how convolution operates? Uh, dense or fully connected layers, as we called it, dense layers in Cross and TensorFlow, uh, learn global patterns. Learn, for example, an apple in an apple, but not its elements. For example, an apple has a leaf, has some texture on it, the shape, something like that. But convolution layers uh, learn local patterns, as we see here. For example, uh, in MNIST, this is MNIST and digit 4. This is digit 4. So as you see, the convolution learns three features in here. For example, a line that like this, uh, a diagonal line like this, a diagonal line like this, and a piece of a line. And it goes on, and it learns this by looking at our, or by just feeding the data set to the model, and the model is going to be trained, and it is trained and learn something. And the convolution also will can learn a spatial hierarchies of patterns. So it can be used somewhere else in other data sets, maybe in other images, in the images on data sets that that our network has never seen. So it is really a useful convolution filters are really useful. You can use them in other things too. So as you see here, for example, the first layer, as I told you in this slide, low level features, high level features, mid level features, and as we see here, the first layer is learning uh, the low level features, like some simple lines, or the nose of the cat, or the outlines of its ear, sorry, yeah, ear. And the last layer of the neural network here is learning more sophisticated and more complex features, like an eye, or the nose, the whole nose, not a part of the nose, or the ear of the cat. So uh, that's it. But there is some problem with convolutional filters, as you see. And you see, we have, for example, in our last in here, we have a 6 by 6 image, and we have a 3 by 3 filter size of convolutional filter size, and we end up in a 4 by 4 image. So it will shrink and it will reduce the image size. We have 6 by 6, but after all, we have 4 by 4. So this is the formula. you know 6, for example, 6 minus 3 plus 1 is equal to 4. And that's the problem, because it shrinks the image size. But we don't want every time, in every layer, in every convolutional layer, we use a convolution filter in every convolutional layer. It will shrink the image. For example, if we have an image of for example, a size of 100 by 100 pixels. After, for example, 5 layers, or no, sorry, 50 layers, for example, 50 layers of convolution filters or convolution layers, we are going to end up with an image of 1 by 1 pixel, or maybe it will just delete the pixel, nothing. We are going to have, for example, a 1 by 1 image that is, the resolution is 1 by 1, but the input image was 100 by 100. So it will shrink and it will reduce the image size. But we have some strategies to mitigate this problem, to control it. Something like padding. As we see here, we have zero padding, because zero padding is like a black border to the image. So the image is going to be a black border image. We have a border around the image, and it will shrink just sorry, just that border. The image is going to be, the resulted image is going to be the same as the input image. So uh, as we called it in Cross or TensorFlow, same or valid. Same is when we have padding, and valid is when we don't have any padding. So that's it. And this is the formula. You don't have to just learn the formula. It's okay. And when we move a convolution, or when the uh, framework or the library or the network is moving the convolutional filter on our images, it is like that. We have three filters for each: red, green, and blue, for each one. But we have another kind of filter or convolved feature. It is like the bias. As you can recall, the equation for a line was wx plus b. W is the weight, x is the input, and b is the bias. So this is the bias, this is the bias. So that's it. And uh, we called these things as feature map or activation map, and we call it a bias map. So this is the name. It's okay to know it. It's better to know it. So, for example, uh, we should pay attention to the number of channels or the depth of the image to the depth of the filter. So they should be similar. They should be the same. If we have a 3-channeled image, we should have a convolution filter with the depth of 3. So they should match each other. And we should pay attention to this, and this. This is the convolution filter. This is our image. So we should pay attention to this and this. They should be the same. And number of parameters in one filter, for example, if, for example, if for example, we have 6, let's say 6 filters 5 by 5, we will end up with 6 activation maps. So the new size of the image is going to be, for example, in this case, we did not have the padding. So you see that the size of it is reduced, and but the depth of it, because of the convolution, the size is reduced, but the depth uh, is increased by 6 because we had 6 convolutional filters. As you see, we had 6 filters. Okay, uh, let's go to these layers of convolution. So we have some other elements in a convolutional neural networks, and as we see, we have convolutional filters, we have pooling layers, we have fully connected layers, and we are going to see what are these things. Convolutional layers in a convolutional neural network summarizes the presence of features uh, in an output image. So a problem with the output feature maps is that they are sensitive to the location of the features in the input. So they are sensitive to the location of the features. One approach to uh, one approach to address this sensitivity is to downsample the features map. So this has the effect of making the resulting downsampled feature maps more robust to changes in the position of the features. For example, of the features in the network. For example, uh, if I have an apple here and the network is trained on my uh, image, and I'm holding an apple in my hand, for example, in this pose, we are going to be have some problems if I move it in and have the apple in that hand, for example. But we are going to mitigate and fight this problem. Um, the approach to address this sensitivity to the location of the feature is to downsample the features. So, uh, it is called as local translation invariance. Pooling layers, as we are talking about now, pooling layers provide an approach to downsampling feature maps by summarizing the presence of features in the patches of the feature map. As you see, for example, we have in the original image, we have, for example, 1, 2, 3, 4, a 4 by 4 image, and average pooling of filter size 2 by 2 and stride 2 is going to end up in a 2 by 2 and 2 by 2. It will just make it the half size of the uh, input image. So the size of it after we apply the pooling, average pooling or max pooling is like the maximum value uh, of each region of our pooling filter. For example, in here 9, in here 7, in here 8, 6. Average is going to be an average of the all values in that region. So that's like it. And they are going to reduce the size if we apply a pooling filter to an image. It will just make the size of the image, the output, the resulted image, it will make it half. For example, we have 4 by 4 image here, and we will end up with 2 by 2. If we have 6 by 6, or for example, 10 by 10. So if we have, for example, for example, if we have 10 by 10 image, an image with 10 by 10 resolution, we will end up by 5 by 5. Okay, we will end up to that. So, uh, two common pooling methods are average pooling and max pooling that summarizes the average of presence of that. So The hyperparameters of pooling filters are the filter size, as we have two, and the stride for maximum for max pooling or average pooling. So F is the filter size and S the stride. Stride is the steps. For example, how much the network is going, the filter is going to be moved each time. For example, if the stride is equal to 2, it is moved 2 pixels. So if the filter is equal to 3, the filter is has the resolution of 3 by 3. If the filter size is 2, the filter size has the resolution of 2 by 2. So this is it, like this. And they are the most common filter sizes and strides. F equals 3 or 2, and strides is equal to 2. So pay attention to this, because we are going to see an example that caused it some problems. Oh, I have something here, so I'm going to clear it. Okay. And let's use convnets with a small data sets. Let's okay, what was using convnets? Okay, using okay, this is it. Let's have some hands-on practice, and you can run it locally on your machines, and it may help you understand these things better. So I just here I am downloading cat versus dog, a dataset. It is a dataset that is on Kaggle website. Kaggle, that is Kaggle. And okay, let's see what is Kaggle. And let me. So this is it. So on Kaggle website. So this is the Kaggle website, and we are going to work with this dataset. And the original dataset there, I have downloaded it and I placed it on my machine, on my PC, and this is it. So I'm going to split it into train directories and validation directories of cats and dogs, and test directories and for that and for dogs and cats. So let me show you what's going on here. And this is it. Okay, data set. Let's see. This is the cat and dog, and this is the data. And I have just split them into these things, these folders. You see, each folder of test, for example, of train and validation contains cats, images of cats, images of dogs. So, and I said that, for example, 1,000 images to be put in test training folder of cats, and from 1,000 to 1,500 to put in validation folder of the cats, and so on. So I have printed the shape and the length. It will print how many numbers are in the list, and OS list dir or OS list directory is going to list the directory, make a list of whatever you have in a directory. So as you see here, this is like this. And so let's go to something more interesting. We created a model by the sequential model creation. So we have a convolutional, two-dimensional convolutional layer, and it has 32 neurons, and the size of the convolutional filter is 3 by 3, and the activation function for that layer is relu. The input layer is going to be 150 by 150 by 3. So the size of the images is 150 by 150 pixels, and they have three channels, three color channels. After that, we have a max pooling two-dimensional layer of the size 2 by 2. So, and after that, another convolutional, another max pooling, convolution, max pooling, convolution, max pooling, and we flat it. So, and we have a fully connected layer with 512 12 neurons with activation ReLU. And the last layer, the output layer, is a single neuron, and the activation is sigmoid function. Because we just want to know, we just want to classify them, classify these images if they are dog or if they are cats. So cat and dog is a binary classification problem. So we need just one neuron and the sigmoid, because sigmoid will return 0 or 1. So and if we get the summary, if we have the summary of the uh, network, it is like this. The first layer is like this. So because in here we have a max pooling. The input size was 150 by 150, but now we end up with 148 and 148 pixels. So you know that's because of the convolution. Convolution reduces the size, you know, but because we don't have any padding here, you know, and max pooling is going to make the size into half. So half of 148 is 47. Sorry, 74. So, and after that, so you see the pattern here, yeah? We have a convolution, after that a max pooling or average pooling. We have a convolution, a pooling, convolutional pooling, convolutional pooling. So it is like a pattern. We after a convolution, convolutional layer, we have a pooling layer. After that, we have flattened those layers, and you see pooling layers doesn't have any learnable parameters or trainable parameters. You see, this is the number of trainable parameters, but convolutional uh, layers have trainable parameters. And flatten, it doesn't have trainable parameters. And after that, we have 512 neurons on our dense layer, and this last layer is another dense layer that has a single neuron, as we see here. So, and after all, we have 3.5 million parameters, learnable, trainable parameters. And we are going to compile our model. We compiled it, and the learning rate is this. The value of the learning rate is this in the optimizer. And we have some data pre-processing. For example, we normalized our values, and this is a data generator. It will just read the data from a directory in batches. For example, the batch size is 20. So it will go and fetch 20 images from that directory and come and feed it to our network. So that's it. And since we use binary cross entropy, we will use binary class mode because we have two classes, dogs and cats. So we have a validation generator like this that flow from directory, and we have we have batch size of 20 here. And we have like this. So for the data, for the trained data, every batch is like this. Number of samples is the number of batch size, is the batch size is equal to the batch size. And after that, the labeled batch shape is going to be equal to our batch size. And let's see how well it performs. So on validation data set, the accuracy is equal to 72%. So we save the model as this, and it will save the model in that directory that the model is running. So uh, for example, in this case, I was running the notebook, for example, in my D drive in some folders. It depends on your choice. So, and let's see here, and you see this is another plot. This is another figure that a comparison between the validation of the training, the accuracy of the training set, and the accuracy of the validation set. On training set, as you see here, we have 98% of accuracy, but on validation accuracy, we have 70, uh, 72% of accuracy. But we see the gap between training accuracy and validation accuracy. So we called it overfitting. We have a big overfitting here. As you see, the difference is like to 26%. So it is a lot. And as you see, the loss is going to increase in validation and decrease in training loss. So this, by looking to it, we see the gap between training and validation. And as here, we see a gap. So, so how can we mitigate overfitting? How can we fight overfitting? By using data augmentation, we have limited numbers of data points or images in this case. So we are going to augment our data. For example, we are going to rotate it from to up to 40 degrees, or we are going to shift the width and the height by 20%, or shear zoom or zoom range. It will randomly do this on our data set, and it will create some, for example, some new data points, some new images. If we have limited images in our data set, so we are going to do this. So in this case, I have just it is not important, so you can just go on. And you see that we augmented the data. For example, this is the same cat. These 4 cats are the same, but every time it is rotated, or it is zoomed, or it is just tilted a little bit. So, we augmented the data. So we have this model again, and we are going to use the model with this with the data augmentation technique. So, and dropout. So we have dropout here, and it will just the value of the dropout is set to 50%. So 50% of the neurons are going to be set to 0 randomly. So we are going to run our model and train it. And after training, we see here, so that's very good, you see, because we don't see any overfitting, and we don't see any gap. The results are really close. So it is really good to see this, that we have 84% of accuracy on our trained set, and on our validation set we have 84%. So, and I saved the model as an H5 uh, format file format. So you see, they are doing really the same on the data that it has been trained on and the data that the network has not seen ever. So it is really good, you see? And so we are going to, sometimes we are going to load some pre-trained models. For example, I was training a cycle GAN model, and it took me a lot of time. For example, around 2 or 3 months to train my model. Because cycle GANs are really they really need lots of computational resources, you know, and it took a lot of time. But sometimes you found, for example, on GitHub or other websites, you find you will find some pre-trained networks, pre-trained models. So there is no need, but you should pay attention that they are trained on a specific data sets. So, but maybe it is useful. Sometimes you can use that pre-trained data, sorry, that pre-trained model. And how can we just load them? So let's see. Load trained model in Keras. So this is this is it. So we are going to call a local model function from Keras from models class and load model function. And you see, I have saved, for example, I saved this model as cats and dogs small 2 h5. I'm going to load this. This is as this simple, and I'm going to just uh, look at the summary of the model, and this is like the model we have here. So it is really nice to load these kinds of things. And model input, model.input is going to tell us what's the input and how can we feed the data set to it. So sorry. And we are going to, for example, uh, use it. For example, we have uh, a very specific, for example, dog here and an image here. And we are going to feed it to the model, to the our pre-trained model. So we just do this. We just model.predict x. What is x? The image that was loaded from the image path here, and the target size. You see if the image here in this path is smaller or bigger than the input size we have for our model, we are going to resize it. But by just feeding this argument of the model, by just setting this as the input as the same as this, so the same as this. So it will it will we will print the model predict here, for example, model.predict x, and it throws something that 50%, the model is sure more than 50% that it is a dog. The class is a dog. Class 1 is dog in this case. So, so, and um, let me check what time is it. So we have time, okay. And so we have symbolic and imperative APIs in TensorFlow. As you can see here, for example, if I want to create and build a model, in the first place, I instantiate uh, the sequential function and class of Keras, as we have imported Keras here. So in this so in this cell Where is it? In this cell, we instantiated Keras under the name of model. So after that, we can add some layers as you see here. Yes, you see lots of, and you can just go to TensorFlow, for example, TensorFlow conv 2D. So you can just read the documentation every time you need to modify the model or create a new model, but you don't know what to do with it. For example, I want to have a 2D convolutional neural network. I'm going to do this. For example, uh, let me just run the first cell. So I'm going to, let's say, import TensorFlow as TF. So I'm going to say, as you see here, tf.cross.layers.convolutional 2D. So for example, I'm going to for example, model is equal to cross.layers, I think cross.functional, cross sequential, for example. It will not suggest. Let me check if I'm just, okay, yeah, model cross. So for example, in this case, for example, I'm going to add some layer. And we know that, for example, in this case, we are working with cross, yeah, for example, cross font 2D. And you have these documentation. You should always work with the documentation, because no one memorize all of the functions. And if you want to know, for example, the arguments of a function, you should just, for example, do this. Let's say, yeah, let's say, for example, this. Let me no module cross. Okay, I have. Okay, so if the problem is this, so where is it? Where did it go? Okay, so from 10 and in earlier versions of TensorFlow or Keras, we can just call it as, for example, from Keras import something, import layers, import models. But now, because Keras is merged together with TensorFlow, we should write this as it is, as TensorFlow.keras import something. Okay. So it is importing and creating the model architecture here. So it is okay. For example, I want to add something else. I just type model.add and layers. So sorry, layers with lowercase l. So layers dot, for example, in this case, you see tf.cross.layers, as we have these layers dot convolutional 2D. Okay, so because we import layers, we can just say layers. We don't have to write these parts, because we imported layers from this part of the TensorFlow package. So you see, for example, conv, and I hit tab, and it will just auto-complete it. So let's get back to what we were saying. So symbolic API versus imperative API. I think it is not really important to know these things, but some benefits with symbolic API, with symbolic APIs, Your model is like a graph, like data structure, as you see here. This means that your model can be inspected or summarized, as we have some summary of our models. Let's say this is the summary of our model in uh, in symbolic APIs, or the sequential, as we have here. Sequential or symbolic is the same. So you can plot it. Maybe sometimes we can plot it, or maybe summarize it. Plot is just draw the network in some really simple diagrams. So you can plot it, or you can summarize it, and and most of the debugging part will happen during the model definition phase, not during the execution in symbolic APIs. So but if you want to use imperative APIs, for example, you have multiple streams of input, as for example, you have images, and uh, you have, for example, features like age, income, postal code, something like that. And beside that, you have images of each person. So you have 2 or 3 or more streams of input. You should use imperative APIs. Uh, so imperative APIs are going to be beneficial here. So let's move on, because we don't have time for today, and I want to reach to neural style transfer, which is here. Okay. Or if we can't, we just we just uh, we just start our next session tomorrow an hour earlier, if you are okay. So if you are okay, please type it in the chat box or say it over the voice, so I know that you're okay uh, to start an hour earlier tomorrow, because some of you said that we are okay. For example, I think Angelica and Aishigul and Eugene told me that they are okay. So uh, everyone, if everyone is okay, we are going to start an hour earlier, but now we are going to continue. So let's see what is data augmentation, as we called. Overfitting is called by having too few samples to learn from. For example, rendering. For example, given infinite data, your model would be exposed to every possible aspect of the data distribution at hand. You would never overfit at that case. In that case, so data augmentation takes the approach of generating more training data from existing training samples. As you see here, we have a fighter jet, and we just rotate it or cut it, or randomly just zoom in or zoom out, or randomly occluded with some shades. So there are some kinds of data augmentation. You see, in Keras, as we have seen, we use image data generator. uh, where did it go? I think this is okay. Image data generator. Overfitting. Okay, I think this was it. No. Okay. Oh yeah, this was. I think yeah. Image data generator is going to just do the data augmentation. If we want to have data augmentation, we use this function in Keras. So sorry. For example, we can rotate it randomly in a range, or we can shift the width and the height of the image, or we can share it, or we can zoom in or zoom out randomly, or flip it horizontally or vertically, or fill it with some shade as we see here, or just do these kinds of things. So we are going to have more training data from our existing data, you see, because we are sometimes we cannot just gather and collect lots of data. It is really expensive or time consuming, so it is not possible for us. And in that case, data augmentation is the best technique to use, using convents with small data sets. I think, yeah, using, what is it? It is like using pre-trained convolution. Yeah, uh, we have just run it. Okay, so we are going to continue. So there are some convolutional neural networks that are so important in this context uh, because for example, uh, and let me say something that is important for in the data augmentation. If you train a new network using this data augmentation configuration, the network will never see the same input twice. So it is another reason to use data augmentation. It is really beneficial. But the inputs it sees are still heavily intercorrelated. So, you know, they are really intercorrelated because they came from a small number of original images. And so you cannot so and you can mitigate overfitting by using data augmentation, or using dropout, or using regularization. So let's go. And we have some important networks in this context because we are going to use some of them. And for example, the first network was LUNET 5, as Jan LeCun created that. And it was like, in this case, grayscale, or a black and white image of MNIST dataset, the digits images. So, and we have some convolutional of, you see, we have a convolutional layer. The filter size is 5 by 5 and the stride is 1. So it will result in 28 by 28 by 5. And we have an average pooling after that. So you see the pattern, a convolution, after that a pooling. So, and we have a convolution here, a pooling, a convolution, and fully connected layers. And we have a softmax. Softmax are useful when we have multiple classes. In this case, we have 10 classes. We are just classifying the digits of MNIST dataset. They are from 0 to 9. So we have 10 kind of different classes. So we use softmax activation function with, and we, for each class, we assign a network, sorry, a neuron to that. For example, if we have 10 classes, we assign 10 neurons to that. But when we have binary classification problems, a single neuron with a sigmoid function is sufficient, and it is good, and we are good to go. But we can use softmax for binary classifications too. But in that case, we should have 2 neurons and softmax activation function. So you see, using sigmoid activation function with 1 neuron is really more sufficient than using 2 neurons. So in binary classifications, pay attention to that. So, and after that, it was AlexNet. As we see it, Alex Krzyzewski on 2012, who won ImageNet competition and who increased the performance by 10%. And it was really fascinating and amazing. So AlexNet is, you see that we have a colored image. So Jan-Luc Lunet 5 in 1989 has a black and white image, but now uh, we have colored image. The size is 227 by 227 by 3 channels of color RGB. So as you see here, this is something strange. I said that it is it is common to use uh, filter size, for example, uh, and the filter size is really big. So you have 11 by 11, the filter size of the convolutional layer, and the stride is 4. It is really jumping. It is not a stepping. It is jumping over the values. So, and it is just convolving the values by 11 by 11. So many a big patch or a big part of our images are involved in every step. So it is not really sufficient, you see, but it was more sufficient than other approaches to AI. And so you see here, after that, we have some, sorry, we have some average pooling that the size and the stride, the filter size and the stride is really strange. So, and we see here that after that we have another average pooling and we have this and the depths. You pay attention and notice the depths of the images that they are increasing, but the resolution and the size of the image is really decreasing, as you see here, 6 by 6 and 256. So after a lot of convolution and convolutional and pooling layers, we end up in these values, this shape, 6 by 6 by 256. So after that, we have 3 classifier layers, classification layers with more than 9,000 and 4,000 and 4,000 neurons on each layer. And after that, we have softmax with 1,000 neurons in our output layer. Why 1,000 outputs? Why 1,000 neurons on our last and our output layer? Because ImageNet dataset has 1,000 classes. So you see the relationship here. And after that, ZFnet was like a modification and to the AlexNet. It makes it better because we see here the difference here between AlexNet and ZFnet was the max pooling, stride, and filter. So you see the stride is 2 and the filter size is 3 by 3. So it is more rational here. But here we have 11 by 11 and the stride is 4. It is really big. So, and we have VGG 16. We will use it a lot. And we have, I'm not going to explain it because it is not necessary and we are short on time. So this is something interesting that they used in GoogleNet or Inception. They use some blocks of convolutional networks inside a bigger network, and they use one by one convolutions. So you see here, they use one by one convolution. One by one convolution is like you have this, every pixel, you convolve every and each pixel. But the reason they did this because they wanted to, without changing the resolution of the image, they wanted to just increase the depth of the image. So the method is called one by one convolution, sometimes called network in network. The pooling layer can compress the width and height, and the one by one convolution can change the number of the channels. So you see there is something genius behind it. And we are going to just, this is the Google Net, and this is, let's see, this is the ResNet. The ResNet is something interesting because they have some skip connections because of the gradient descent. And sometimes if the when the networks before the ResNet, the deep neural networks, when they are going to get deeper, they got saturated in terms of gradient descent, and they cannot uh, be converged, or they would diverge because the weights are not going to update appropriately. But they make some skip connections. It was like, for example, some canals, for example, a village here and another village here and another village here and another village here. And you see there is a stream of water coming all this way, and the water is like this. And the village, the first village is going, for example, the first village is our first layer, for example, for our first group of layers. The first village is going to consume lots of water, drink lots of waters, or they will just water their farms a lot because they are the first village and they have lots of water, they have lots of resources, you know. And the second village is going to have less amount of water in comparison with the first village. And you see the last village is going to have no water at all. So it is like, that's what I say in terms of gradient descent and getting saturated and diverging or not converging, maybe not converging is better. But in ResNet, they created something, they called it skip connections. For example, from this part, they skip something, they make some canals, some water canals. So the water can flow here. It was not, of course, water. This is an example. So uh, the weights of last layers here, for example, let me clear it. The weights of these last layers, these layers can be updated appropriately. So the network can become more deep. So we can have more layers, for example, after that, because I think the ResNet architecture has around maybe um around 150 layers. So it was a lot according in comparison to, for example, VGG 16 that has only 16 layers, or for example, AlexNet that has, for example, 1, 2, 3, 4, 5, 6, 7, 8, 8 layers of convolution, for example. And let's just see how using a pre-trained convolutional neural network is like. So, okay. So here it is. You can download VGG 16 weights if you cannot download it from if it doesn't allow you to download it maybe sometimes, but it's okay. We can just import it here, and we can import pre-processing image class, and we just have it by, for example, like this. We have the model VGG 16 here, and the weights are ImageNet, the ImageNet dataset. So we just loaded that that kind of model, VGG 16 model, that is trained on ImageNet. So this is the summary. You see the input layer. We have two convolutional layers. After that, we have pooling, convolutional pooling, convolutional pooling. So lots of convolutional and poolings. After that, we have a flatten and dense, and we end up with 150 around 140 million trainable parameters. So it is a lot, you see. And we can just, for example, uh, I have an image of a dog. Let me just, for example, let me, um, so it is not here. I'm not sure if it is here yet. So this is the dog image I have, and I feed it into I evaluate the model on that dog, and I feed the image to the data set. And you see here, I got some predictions, and I asked the model to say what it was. And the ImageNet has lots of, for example, it says that I'm 99%, 99.9% sure that this image is a dog. So, and so it is a little chance that it is a Malinois uh, race, and it is a Kelpie. It is, I think it is very, very little chance that it can be a Kelpie. But there is a very good chance that it can be a German Shepherd, for example. But if you have any other, for example, if you have any other kind of thing, so ImageNet is has a thousand classes. For example, you can see that it has lots of classes, as you see, for example, dogs, shapes, cars, everything. So yeah, you can work with ImageNet really good. So let's be back to this. Okay, I'm going to just let me um so we are going to not to work with this because we are not working with regression problems in this workshop. And let's go here. So okay, so we reached this part that generative deep learning, and the main part of our workshop is about these kinds of things. So in the summer of 2015, we were entertained by Google Deep Dream. Let me just bring it forward, and this is it. Okay, this is the output of Google Deep Dream. I think most of you saw the videos of it and the images, and how psychedelic and how strange it is. It was trained on dog faces, and you see we can see some dogs here, and this algorithm, Google's Deep Dream algorithm, um, turning an image into a psychedelic mess of dog eyes and periodic artifacts. In 2016, we used the Prisma, I think the application Prisma that uh, it was, let me bring it forward. Okay, the Prisma application, uh, it turns our photos into the paintings of various styles. If you use it, it in a matter of seconds, it use some AI to just make our photos into paintings of various styles. So in summer of 2016, another example for deep generative deep learning is this movie. This was a movie in 2016, uh, an experimental short movie. It was called, I think the name was, um, Sunspring. Yeah, it was Sunspring, and it was directed using a script written by long short-term memory, or in short LSTM algorithms. It is a kind of AI algorithms that it was completed with dialogue, and so it was the first movie, I think, that the script was written by an AI algorithm. So the AI was really like there were some breakthroughs. AI isn't anywhere close to rivaling human screenwriters, painters, uh, composers, but replacing humans was always beside the point. Artificial intelligence isn't about replacing our own intelligence, with with something else. It is about bringing into our life and work more intelligence of a different kind. In many fields, but especially in creative fields, AI will be used by humans as a tool to augment their own capabilities, more augmented intelligence than artificial intelligence. For example, we uh, we are architects, I mean, or designers, we should be some creative persons. So AI is going to help us in different ways. It is going to bring some kind of different intelligence into our work. So using AI is really amazing. So let's go to neural style transfer. Uh, Neural style transfer was introduced, I think, in 2016 by Leon Yatis. In this context, a style essentially means textures. So colors and texture and visual patterns. It is what we call a style in this context in an image at various spatial scales, and the content is the higher level microstructure of the image. For instance, blue and yellow circular brush strokes are considered to be the style in, for example, a Starry Night of Van Gogh. Yeah. So that these blue and yellow circular brush strokes are considered to be the style in this image. And the building here, for example, buildings, buildings in these, for example, in these images, or in these photos, are considered to be the content. The key notion behind implementing a style transfer is the same idea that's central to all deep learning algorithms. You define a loss function to specify what you want to achieve, and you minimize this loss. You know that you want to achieve what you want to achieve. Uh, Conserving the content of the original image while adopting the style of the reference image. If you are able to mathematically define content and style, then an appropriate loss function to minimize would be the distance between the style of the reference image and the style of the generated image, plus the distance between the content of the original image and the content of the generated image. So here the distance is a normal function. So, you know, uh, let's go to this, uh, let's go to have neural style transfer. So what we are having here, neural style transfer. Okay. Um, so as you see here, the content in this picture is the buildings here, and their style is the blue and yellow uh, yellow brush strokes, and the combination image is going to be like a painting, but from that image. So we can use, for example, we can have a screenshot of the Rhino uh, environment, and we want to just make it like, for example, Miyazaki. If you know Miyazaki, he's a Japanese animator. He's really great. His works are really great. Maybe uh, some some buildings or some styles in their works. For example, let me move the move the zoom controls. Okay, you see that this style is something interesting. We can have an image, a screenshot of the Rhino environment that we are working on a model, but we don't have the time, for example, or we don't have the resources to render it, or we cannot render it in the style we want. We can use the neural style transfer here. For example, let's assume that this is a, a screenshot of Rhino environment, and this is a Miyazaki building like this or this or this, or what other uh, image you have in mind, or for example a Van Gogh painting, whatever you want. As this is, for example, I have the target image and the reference image. Target image is going to be for example in here, let me see, as you see here. So the target image is going to be something like this. For example, let me find it. I just have it as the target image. It is Slavoj Žižek. He's a philosopher, and the style reference image is going to be something like that. So after training it, so you see, you just have to, if you download the code from my GitHub repository, you just have to specify your target image path and your style reference image path. Nothing else. So you just have to run these cells and go through this, because we are going to use VGG19. So it is a transfer learning style. And we just, I have just created this function so you can use it. And we are going to have some images like this. Okay, we are going to have something like this, or we can, let me find it. Where is it? So let me find the image that I have created. So let's see the notebooks here, the images. Okay, I have something like this. I have I feed the network some image of San Francisco, I guess, and the Starry Night painting. After lots of, let me go, okay, let me go to the last image so you can see. After 4,000 iterations, it end up in something like this. So you can just download the code, and you can just place the target image as, for example, in this case, I showed you uh, some buildings, for example, buildings. You can say something like that. You can have a building and uh, the style reference image pass some other uh, some let's say, for example, the Starry Night or some other painting or some Miyazaki artworks as the style reference image. So you can just transfer the style of those images, that target image, to this reference image, for example. You can do this, and we are good to go, I think. And let me check the hour. So, okay, it is 4:30. I think we can end today's session, and we are going to just start an hour earlier tomorrow. So we are going to start 9 a.m. New York time. Uh, if you don't have any issues with that, if you don't have any problems with that, I'm going to work with, let me say, I'm going to work with uh, something like a StyleGAN version 2. Let's say, where is some, okay, this is it. For example, this, and this. We are going to see something like this if it can be downloaded. Okay. We are going to work with StyleGAN version 2 and maybe VQGAN, so those kinds of generative adversarial networks. And tomorrow is going to be some hands-on session, so you can see that it is going to be downloaded because it is around 30 megabytes of image, and Google Drive is really slow. So
They're not
maybe
able
I
to
go to
see
my
it.
Google Drive. Yeah, and so let's go to Google Drive. I think, no, it is not downloaded. So let's go to here. I need your emails. I will add you to my Google Drive so you can just access the code. And we are going to have an exciting session because this session was really about more theory. And for example, here, and this one, if it is going to be loaded. I just train it on a small data set. You can gather a good data set, or you can go and crawl the network. I just, for example, you see, where is it? I just, the data set of mine was just like this. I don't know where I put it. Data set. Okay. Um, I downloaded some images from ArcDaily, and you see uh, the data set is the exterior of some buildings. And we are going to see that we are going to have some new formations of the facade on an exterior of buildings next day. But you can do this on your on the plan view of your networks, or maybe the interiors. It is it depends on you, on what you want, but we are going to work on this. And after that, we are going to work, for example, on VQGAN. Let me show you some examples here. For example, uh, this is a Japanese city in 2100 in that year, for example, and this is the VQGAN. So, or for example, I have a future Paris, I think, yeah. For example, this one, and we are going to uh, work on both of them. For example, we are going to feed the output of the style GAN to the to the VQ GAN. So it is going to be something special, something that we have. I have another meeting in 15 minutes and should have. Okay, yeah, I'm going to end this meeting, end this session. So if you don't have any question, I'm going to end it. So
actually, I have a very simple question.
okay.
I downloaded the softwares, but for the Python, I think I downloaded 3.10. And when I go to 3.8, I downloaded the files, but I'm not able to install it as far as I understand.
So can you share your screen maybe? You can just go to python.org, python.org, and you can download the appropriate python.org, and you can download the appropriate version of Python.
You need to, it's disabled,
yeah.
The screen sharing is disabled.
It is disabled, so let me